Welcome everybody. It's a great pleasure to introduce Professor Ole Warnaar from the University of Queensland. Ole and I were together in 1990 working in the Institute for Theoretical Physics in Amsterdam. Ole is a fellow of the Australian Academy of Science and has made various lovely discoveries in both statistical mechanics and special function theory. And he also happens to be the current president of AustNS. So over to you, Ole.
Thanks, John. It's a pleasure to speak at Number Theory Down Under. I'm going to tell you a story about, well, some interesting functions that certainly have some interesting connections to number theory, but I really wanted to give a little bit of background where these functions come from. And unfortunately, that is not very number theoretic. So I hope you'll bear with me, even though I'm going to take you outside perhaps your comfort zone and talk about some things that live in a different world. And there's a lot of jargon and notation there, which I'm not going to explain. So this first motivation, it's really to just give you an idea where the things that I'm going to look at, where they naturally live and how they naturally occur. But I'm certainly not assuming you'll follow everything that I'll be saying here, but hopefully something will stick. And so the world that I'm going to be looking at is the world of infinite dimensional Lie algebras. And to many of the things I'm going to say, they're true for arbitrary Kac-Moody Lie algebras, or at least of affine type, but I won't have anything to say about those. So I'll restrict myself to sort of the simplest type of affine Lie algebra, which is essentially affine version of SLN. Okay, so and if you know what that thing is, great. If you don't know what it is, don't worry about it. Okay, but what I guess when you're doing algebra, typically what we're interested in is representations and representation theory, and that's the objects that I'm going to talk about today. And so that's essentially characters of representations of these affine Lie algebras, or in particular characters of representations of the affine version of type A Lie algebras. Okay, so it turns out that these, I'm not going to exactly explain what these things are, but it turns out that they have very interesting connections to questions about, well, modularity. Okay, so let's just accept that there are these characters of irreducible representations, and in particular, a very important class of representations of these affine Lie algebras. They are known as integrable highest weight representations. So this is probably the most important class of representations. In a moment, I'll actually enlarge this class slightly, but let's for the moment stick to these integrable highest weight representations, whatever they are. Okay, and there is a well-known formula. You can actually compute the characters of these representations using a well-known formula due to, well, in the affine case to Victor Katz, and in the classical case to Weil, and which is now known as the Wildcats character formula. And the great thing about this Wildcats character formula is that you only need to know sort of data coming from the underlying root system. And I've given you a little picture here. The picture is a lie, because I'm interested in affine Lie algebra. So everything is infinite dimensional. And I've drawn here a little picture for you, which is the non-affine case, but it's still type A, and this is in fact SL3. And so but structurally everything is the same. So this picture already conveys a lot of what's going on, but the picture is nice and finite dimensional, so I can actually show it to you. But morally, in the affine world, things are exactly like this, but then everything becomes infinite dimensional. So here you see a representation. And so you see this, in particular, these blue vectors, well, they're the positive roots of the root system. So you see there's this cone here, and essentially these integrable highest weight representations, what it says is that at every lattice point here in the cone, there is a unique irreducible representation. And in particular, the sort of topmost dot in that cone is the highest weight of that representation. So here, this is a highest weight representation represented by this little vector just in some Euclidean space. And in that representation, there is a nice decomposition. So I'll go back to my earlier slide, where this module, it breaks up into smaller spaces that are known as weight spaces. And essentially these characters, they just are generating functions where they encode the dimensions of the various weight spaces that occur in this decomposition. So here are the weight spaces, here are the weights in the weight space decomposition. So you can see exactly, well, 1, 2, 3, 4, 5, 6, 7 dots. So there are 7 weight spaces. And this dot in the middle is slightly bigger because it in fact has dimension 2. All these smaller dots have dimension 1. So you're looking at an 8-dimensional module. That's of course finite dimensional. As I said, in the affine case, things become infinite dimensional, but it's a similar idea. And if you take another dot in this cone here, you get another representation and so on. Okay, so that's the kind of thing we're studying. But it turns out that if you normalize these characters, and again, what this normalization factor is not important. There's a lot of notation that I haven't explained, but the term here, modular anomaly, is already giving you a hint. We're normalizing this thing such that this normalized character has really nice modular properties. And so that's sort of the, I guess, surprising discovery by Katz and Peterson. They showed that these normalized characters, they're essentially Jacobi modular forms. So again, let's not worry about all this text here, but if you just look at this formula here, you see a character, and so it depends on a bunch of variables, tau, z, and u, where z is a r minus 1-dimensional set of variables. But you can see it transforms. So you take one of these characters, you carry out here this modular transformation, and you can essentially express it again as a linear combination of characters. And the modular S matrix, which is really what governs these modular transformation laws, they're explicitly known, and there's many things you can say about these modular matrices. They're very, very interesting in themselves, but I'm not really going to talk about them here. But we know what they are explicitly. So for example, for F1 SL2, here I've given you an example of what this modular S matrix looks like. So it's just a matrix with trigonometric entries, for example. Okay, so I guess the bottom line is that if you study characters of infinite dimensional Lie algebras, you're naturally end up with functions that have great modular properties. Now, this is the theory of integrable highest weight representations, which I said is sort of the most important class of representations. But it was discovered after the work of Katz and Peterson by Katz and Wakimoto that there was a larger class of representations that, so they were no longer integrable, whatever that means, that was still modular. So in other words, they realized that you could find other representations, more complicated representations of these infinite dimensional Lie algebras. If you compute the characters of those, you still had these Jacobi modular forms. And so they called these representations admissible representations. And I'm interested in particular in the branching functions of these admissible representations. So what are those? Well, you take essentially, I do it at the level of the characters, but you take tensor products of irreducible representations, but now these representations no longer have to be integrable, or at least one of them can be admissible. You expand this in terms of, again, characters, and then up to some powers of q that we don't care about, where q is e to the power 2 pi I tau, I should say. You get some functions, these coefficients here, and they're known as branching functions. And again, it turns out that they have very interesting modular properties. Not that surprising, because we are taking two interesting modular functions, we multiply them together, we expand them in modular objects, that these coefficients in this expansion also have something to do with modularity. Okay, so again, that's probably all I want to say about this. And in particular, these branching functions, well, one surprise is that they correspond to characters of another type of algebras that I I have no time to talk about, and it would be outside the scope of this I guess, conference. They're W algebras. So if you're familiar with the Virasoro algebra, W algebra is sort of a higher rank generalization of the Virasoro algebra. But again, these branching functions have very interesting modular properties. And so here I've given you an explicit formula for these branching functions in this expansion formula. And the point is that you can see I can express them as products of Jacobi theta functions. So, well, that already indicates that there is a lot of sort of arithmetic things that should be going on. And so let me give you a little example where I compute some of these branching functions. And here I've called them H and G, because it turns out that in this particular very simple example where I compute these branching functions, these functions are the well-known Rogers-Ramanujan functions for those who have seen these before. And there's a lot of arithmetic information that is encoded in these functions. So for example, well, you have nice transformation properties with respect to, well, this particular congruent subgroup of the modular group. The ratio of this G and H, you can express this really, really nicely in integrals over the Dedekind eta function. And for example, these functions, they are algebraic units in some imaginary quadratic field. So there's a lot of arithmetic things you can say about these things. In particular, so again, this is the ratio of this H and G was already studied by Ramanujan. Of course, not in this context of branching functions of infinite dimensional Lie algebras. And he in his second letter to Hardy already stated some of these values of this function in terms of these beautiful sort of formulas, including the square roots of 5. So these are famous results. And this little, at the bottom of this slide, you can see this was from the second letter of Ramanujan to Hardy. So you can see precisely these Fi, and sorry, this should not be an I here. This second formula here, this I here should have been I plus 1 over 2. So that's a clear typo. These two can't be correct simultaneously because I've add them up, then the left-hand side would give me 0. But in any case, so these functions are very interesting. As I said, they come from the study of infinite dimensional Lie algebras, but there's a lot of interesting number theoretic information, a lot of interesting arithmetic properties that these functions have. And in particular, so and I know that I've lost everyone, but I'll soon change gears and I'll just and make things hopefully more understandable. As I said, these branching functions can be expressed as products of Jacobi theta functions. So, but in this particular example that I've shown you, so that's sort of these G and H, that is these infinite products you see here on the left. But from what are known as the Rogers-Ramanujan identities, they have these Eulerian forms as well, which are manifestly positive, and they give us a lot of information about the underlying representations. So in particular, having these manifestly positive Eulerian forms tell us a lot about the underlying representation theory. And so we would really like to have these kinds of Eulerian forms for these more general branching functions. This is a very special case here where R is 2, so that's just SL2, and D is 3, so D, we call that a level. So in a very trivial case, we understand everything, but in general, we understand very, very little. And so that's sort of where the main question for this talk comes from. And so this is notoriously difficult. Find manifestly positive or Eulerian representations for these more general branching functions. So set these functions, they're very nice modular functions. They have a lot of arithmetic information, but we don't really understand them very well from the representation theoretic point of view, because we don't really understand the sort of manifestly positive representations for these functions. So that's such as we know in the case of Rogers-Ramanujan. And even in the case of Rogers-Ramanujan, this already led to many important other discoveries, such as vertex operator algebras, and which ultimately, I guess, played an important role in monstrous moonshine and things like that. So these are really important questions. Okay, well, so that was not an easy start. So let me now slow down. But in any case, so this is the question that I'm interested in. I want to understand these branching functions better, but perhaps not doing too much affine algebra theory, because that would be somewhat off topic. Okay, so I'm going to go to back to just some, well, elementary partition theory. So hopefully everyone knows what a partition is. It's just, right, a sequence of non-negative integers that is weakly decreasing. And here I have an example of a partition 5, 3, 2, 2, and 1. So that would be a partition of the number 13. And I like to think, certainly for this talk, I like to think of a partition as just the stacking of some unit, well, squares here. So, right, 5, that's just 5 squares in the first row, then a 3, that's 3 squares in the second row, and so on. Okay. And then, of course, the number being partitioned, that 13 is nothing but, because these are unit squares, it's nothing but the area of this little diagram, for example. And it was already known to Euler that if you try to compute the generating function for these integer partitions, where max is just the largest part, so the max in this example would be 5, the partition being partitioned is 13. So instead of this, I could also write the area of that partition. You just get some nice infinite product. Okay, so as I said, that was known to Euler already. And we'll see this function f showing up much later in the talk. So, but not for a little while. Okay, so still with partitions, as I said, I represent partitions as a diagram. Now, of course, what I can do with this diagram, I can just rotate this. So rather than a diagram where the largest part is at the top, I might as well put the largest part at the bottom. So I just rotate this by 180 degrees. So now this is the same partition 5, 3, right? This is 5, 3, 2, 2, 1. So it's essentially the same partition. And I can just represent this as a lattice path, so as a dict path, starting at the origin and ending in some box or in some corner A, comma B. And what is this area? Well, what I can do is simply keep track of the height of this walk here. So here's height 1, 1, here's height 2, here's 4, and here's 5. And of course, if I add up these numbers, the sum of these y coordinates, so that's sort of the height where I'm at, you precisely get 13. I hope I do, if I didn't make a mistake, but I think that's correct. Okay, so the generating function of partitions that fit inside a box or a rectangle of dimensions a comma b, well, I can, by definition, I call that the q-binomial coefficient. And so that's just, right, the sum over all paths from the origin to a comma b, where the weight of a path is given by the q to the power the sum of the y coordinates. And again, it has a nice infinite product. Well, I shouldn't say an infinite product, a finite product here, not infinite, of course. This is just a polynomial. It's also known as the Gaussian polynomial. And again, we'll meet this q-binomial coefficient a little bit later. Okay, so that's just partitions. So we need to go to a higher dimensional version of this. So now I need to study, rather than partitions, I'm going to look at plane partitions. So I do exactly the same as in the case of partitions, but let me just skip this page and do it in a picture. So rather now than stacking squares, I'm stacking unit cubes. So just look at the bottom of this page. And this is an example of a plane partition. Of course, an equivalent way of viewing a plane partition is just an ordinary partition where you fill in each of these boxes or each of the squares with a number. And this number 4 would just mean that you're in fact stacking 4 unit cubes. In this position, 4 in the second position, 3 in this one, and so on. So you can see that this diagram here represents exactly this stacking of the unit cubes that you see down the page. Okay, so this is now a plane partition. And of course, again, you have the same weakly decreasing condition. So if you start at the top corner here of your plane partition and you take a walk, then you should always be going either flat or you should be going down, and doesn't matter how you walk away from that point, it should always be like that. Okay, so you can formally define that. That's what I did in this previous page, but that's not that important, right? It should be clear what a plane partition is. So this is just a higher dimensional analog of the integer partitions, and this is what we need. And well, this, like the Euler formula for the generating function of ordinary partitions, there's a very nice formula for the generating function of plane partitions. And it looks very similar. If you remove this n here on the right, then you precisely get Euler's formula. Okay, and where this trace is now, so essentially if you go back here, the trace is just you sum up the entries along the main diagonal, or in this picture here, 4 and 3 here. So the number of boxes in this, what I call again the main diagonal of the plane partition, that's the trace. And then of course the volume is q, this pi, or the size of the plane partition, that's just the volume of the number of, so in other words, the number of unit cubes that you stacked. And if you compute the generating function, you get again something that's very pretty. Later, I'll slightly change this trace to the max. So that would simply be the max in this case would be 4, because the maximal number of cubes that I've stacked is 4 in any column. So there's no pretty formula for that, but it turns out that this is actually a really important statistic. And so keep that in mind, and I'll talk about that later in my talk. Like in the case of partitions, where I said, oh, we can put partitions in a box, and then you obtain the Gaussian polynomial of Q binomial coefficient. You can do the same thing here. You can put plane partitions in a box. So this is, McMahon already did that. So this is a picture of box plane partitions. So now you have, of course, 3 dimensions, A, B, and C. And this is a plane partition that fits in that box. So there it is. And McMahon, I mean, I think this is a very beautiful, it's one of my favorite formulas in sort of combinatorics or additive number theory. I think it's extremely pretty that there's such a nice formula for the generating function of plane partitions that fit in a box of dimensions A, B, and C. Of course, it's obviously symmetric in A, B, and C, as it should, because you can take this picture here at the top of this page, and if you start sort of rotating it, of course, it doesn't change the generating function, because only thing you care about is the volume of this stacking of unit cubes. Okay, so that's a really pretty formula. There's also a number of symmetry classes of plane partitions. So here's, for example, one, this is known as symmetric plane partition. So you can see if this picture here, if you reflect this in the main diagonal, so what you see on the right is the same what you see on the left, okay? And again, it's a beautiful formula, which is again due to McMahon, but they couldn't prove this formula. So this is much harder than, this one was proved by McMahon, this one was only conjectured by McMahon, and took, I think, 60 or 70 years before it was actually proven. But that's not the story of today, but there's many of these nice formulas around for these plane partitions that fit in a box, and for the various symmetry classes of these. Now, how would you compute the generating function of plane partitions, whether it's with or without symmetry? And so essentially you can just repeat what I did earlier with the Q binomial coefficient, which I represented as a Dick path starting in the origin and going to some fixed point. So here, what we can do is, so here's a picture of a box plane partition on the left, and I can simply draw these lines. So I start at all these positions sort of on the red here at the top, and I just draw lines, I just go down and I just follow these essentially the structure, the cubes here. And so you get this selection of black path that you see on the right. It's obviously this is in bijection, right? So in other words, here is that same picture again. I extend these paths a little bit on top here and here at the bottom. And then I rotate this figure a little bit, hopefully, right? I'm not going to explain the exact details, but hopefully you can see that all these pictures, you can go from the left to the right or from the right to the left. And so essentially the upshot of this little bijection. So again, we started with a box plane partition, and now we have a set of dict paths in a rectangle here. And if you want to get the volume of this plane partition, well, you again just need to keep track of the heights of the horizontal steps of the various dict paths, and you get exactly the same, you get the same number. So in other words, the generating function for box plane partitions, where the absolute value of pi, that's just the volume or the number of unit cubes, well, up to a trivial factor here, which is because of these red bits that I have put in here so that it fits nicely into a rectangle, but that's a trivial factor. It's just a generating function over this set of dict paths with fixed starting positions and fixed ending positions. Okay, so any such picture will correspond to a plane partition. Now, it's not so easy to compute the generating function of this collection of dict paths because these paths are actually non-intersecting. So they're trying to avoid each other. So it's never possible even to touch. Okay, so for example, well, here we have near touching, but that's as close as you can get. Okay, and that's precisely because we started with a plane partition. So these lines can never touch each other. So we call this sort of non-intersecting paths. So that makes this a difficult combinatorial problem. If these paths could just intersect, then it would be trivial, and you can probably give it to, I don't know, a bright high school student or a first year undergraduate student to figure out the number of these configurations. But the non-intersecting property makes this a difficult combinatorial problem. So there's a little trick that you can do to make this into that easy problem that everyone can solve. We just ignore the fact that all these paths should not intersect, and we just throw in the collection of intersecting paths as well. So here is again a collection of paths, but this of course does not correspond to a plane partition because these paths, they don't just touch like you see the blue and the red over here, but they even intersect like over here. Okay, so this is certainly a bad configuration and it shouldn't occur. But what you can do is to each such picture, you can attach a permutation. And essentially the permutation encodes, so here I start with the first path. So in a non-intersecting path, because it's the first here, it should also reach the top before any of the other paths. So again, if you go back here, this first path reached the top first, the second path obviously reaches the top second, and so on. But here the order can be all wrong. This first path, for example, reaches the top, or its finishing point in third position. So we can encode that in a permutation. And the point is that any such configuration that is not good, like this one, we can match this with another configuration that is not good, but that has a permutation with a different sign. So every permutation has a sign, or just -1 to the power of the length of the permutation. And so how do I match this one up? Well, here it is. I just take the first time that a crossing occurs or a touching occurs, and I just swap these two around. And the effect of this is that everything else is the same. The heights of the horizontal steps, they are in the same position. So it has the same weight, this path, but it has a different sign. So these two pictures, they're just going to cancel each other out because I've swapped these two paths. So you see the slight difference at what happens at the top, and these have different permutations with a different sign. So if I take the signed sum over all these paths, then all the bad paths, they just cancel out, and I'm just left with the ones that I really should be counting. But now things are easy. So, right, so here we have the generating function of plane partitions. Well, that's can be represented as summing over all these non-intersecting paths. That's too difficult. We just throw in all the paths, but we keep track of the sign. We know that all the bad paths, they just cancel out. But now because of this, essentially all the paths, they just become completely independent of each other. So there's a little bit of technical calculation here. So let's just skip this. The point is that this is precisely a determinant. So all you need to do is just evaluate this determinant, and you have in fact found the generating function of plane partitions. So this is again this same Q binomial coefficient. And computing this determinant, it's maybe not an exercise for a high school student, but it's maybe an exercise for an honor student to compute this determinant. It's not super hard. And so you precisely get McMahon's formula. So it's just a classical determinant evaluation. Okay, so far, what does this have to do with my first sort of 10 minutes of talking about these modular functions arising in representation theory? So far, of course, there's no obvious connection. And in fact, there isn't. But these plane partitions, they certainly have a connection to representation theory. So we're sort of on the right track, but not right enough in a sense. So for example, this generating function of box plane partitions that I've been talking about, you can actually show that this is known as the sort of the Q dimension, whatever that is. If you know what it is, great. If you don't know what it is, it doesn't matter. It is some object that is well known in representation theory. So the message is that these plane partitions indeed encode representation theoretic things. Unfortunately, it's all finite things. So in particular, this corresponds to polynomial representations of GLN. And I really want to go to the affine world. This is still the world of classical groups. Okay, so I'm not quite there yet. Another example, so I mentioned earlier, the symmetric plane partitions. Again, it turns out that indeed this has something to do with representation theory. So in particular, this now corresponds to a Q dimension formula that arises if you in sort of the branching problem for classical groups. Again, if you know what that is, it's great. If you don't know what it is, the message is that these plane partitions are connected to representation theory, but unfortunately, we need to go to the infinite dimensional world. And at the moment, we live in the finite dimensional world. Okay, so we have made a small step, but the step isn't quite, well, large or big enough, and we need to enhance our plane partition model and hopefully get to the things that we're really interested in. So this is sort of the question. Are there plane partition analogs that really model things for affine Lie algebras? Okay, because as I said, we're in the world of classical groups and classical Lie algebras. We want to go to the affine case. And if this has an affirmative answer, then the follow-up question is, well, will this actually really help me in understand these modules coming from these W algebras or these type A branching functions? Because it's one thing to find a connection with affine Lie algebra representation theory. It's another question if it's actually precisely the objects that I talked about at the very start of the lecture. And of course, both of these questions will have an affirmative answer. Otherwise, I wouldn't be telling you this, I guess. So we need something fancier than just plane partitions. Unfortunately, they were introduced in the combinatorics literature about 25 years ago. So probably about 100 years after McMahon introduced plane partitions. And so they call these things cylindric partitions. And here's a picture of a cylindric partition. And I'm not sure I really like the term cylindric partition. I would have preferred them to be called something like affine plane partitions, right? Because after all, we want to go from Lie algebras or Lie groups to affine things. And this is very much an affine analog of plane partitions. In any case, they called it cylindric. So how do you define these things? So we're fixing two integers, r and d, where r is, I'm going to call that the rank. And this r is going to be the same as the r in SLR or in affine SLR. And d is the level, which is essentially going to be the same as the level of the representations, if you know what the level is. The higher the level, the more complicated your representation. And so now a cylindric partition, essentially the idea is it's a plane partition that you've wrapped around the cylinder. So if you want to be able to do that, so let's, I know this is bad practice, but I'm walking back to an ordinary plane partition. So here is a plane partition, and I'm taking this picture here. Okay, so rather than the unit cubes. So here's a picture of a plane partition. If you want to wrap this around a cylinder, well, you have a problem because, right, this last row is only length 1. If I start to put this on top, well, that's not going to work because I need to be weakly decreasing if I go down. If I put this 1 here on top, for example, I have a 1 followed by a 4, that is just no good. Okay, so a trivial wrapping just doesn't work. So the idea that they had was, well, what you need to do, you need to offset the rows. So rather than the rows just being on top of each other, each row has a little offset. So this 2,1, for example, you could push it slightly to the right. And this 3,2, you push it slightly to the right as well, and so on. And now, when you also put this last one back on top, you also push it to the right, and you push it to the right sufficiently far. So, for example, that this 1 will not end up on top of this 4, or not on top of this 4. But for example, it could fit here on top of this 1. Okay, so that leads naturally to this shifted or offset plane partitions. So if you forget about this top row here, this is again a plane partition, that each of the rows is offset to the right. And now the cylindric bit or the affine bit is really taking this bottom row and putting it back on top, but again, offset to the right. And you can see that whenever you walk down, you're always going to be weakly decreasing. And of course, you should think of this third row now being again on top of this here. So it's really an infinite picture. That's why you should think of this as wrapped on the cylinder. And if you do this same picture here, so this corresponds to this. So here I've done it in terms of the stacked unit cubes. So, right, so you now have essentially this pattern starts to repeat, but whenever you walk down, or whenever you go down like this, you're always weakly decreasing. So this is an example. So I haven't really formally defined for you what it is, but hopefully you get some feel for what a cylindric partition looks like. And this profile here, that's essentially, it encodes these offsets, right? So a profile here would be 2201, and that just tells you how much each of these rows is shifted compared to the next row. Okay, and then this D here, this level, is just the sum of these offsets. So you can see that in this picture here. All right, you can exactly repeat this non-intersecting lattice path method, but now, of course, it's a little bit more complicated. You don't get a determinant, you essentially get a sum over determinants, because rather than a sum over the symmetric group, you in fact end up with a sum over the affine Weil group, if you know what that is. And so, but the upshot is that there's again a nice closed form expression for the generating function now of cylindric partitions of a fixed profile. And well, here it is. It is a sum over some determinant. Let's not worry about it too much. Turns out, so here I have the generating function where the max of the cylindric partition, so that is nothing but the largest number of cubes that I've stacked, so it's 11, or in this here, the height of this highest column, which is again 11. If I let that go to infinity, it turns out that I precisely get a product over Jacobi theta functions. And if you remember, which I'm sure you don't, but if you remember the expression that I showed at the very start for these branching functions corresponding to these admissible representations of the type A affine Lie algebra, it was exactly the same product over theta functions, provided I make a slight identification of the parameters I used over there and the parameters I use over here, except for a simple factor of Q infinity. So it's a very simple factor, which is essentially, hello, John, having some company there. So it's essentially just up to a Dedekind data function. This is precisely a branching function of these admissible representations. So that's quite magical. So not just do we have the correct model in terms of these cylindric partitions, but it really gives us, so that's sort of an affine analog of these plane partitions, but it really gives us these objects that we were interested in. In particular, as I showed earlier, the Rogers-Ramanujan functions are just a very special case of this. All right. So, well, so is this helpful, this model? So that what does it mean? What have we really achieved? Well, what we have achieved is that we have a combinatorial model that computes for us these branching functions in terms, so the model is just these cylindric partitions. But these cylindric partitions, they're really nice to work with. So now I'm going back to the generating function where I keep track of the maximum part, so z to the max. So in this example, again, the max would be 11, and q to the, again, the volume of the cylindric partition. Let's try to compute this. Now, that's not so easy to compute this generating function. Earlier, I computed this, of course. I said, well, you can do this using these non-intersecting paths, but not if you keep track of the max. So you need to do something different here. But the great thing is that you can, if you take this cylindric partition here, there's only 3 possible positions where the maximum entry can occur. It must occur in one of these corner boxes, as they're called, on the left, right? Simply because of the weakly decreasing condition. So because you're weakly decreasing if you walk to the right or if you walk down, only these boxes here. And of course, this 9 here is the same as that 9. So it's not colored again. This is also corner box. And again, this is a finite snapshot of an infinite picture. And what you can do is you can play around with these corner boxes. If you remove one of them, you get a new type of cylindric partition with a slightly different profile. And essentially what it does, by looking at all your options of removing boxes in the corners or removing the max, you can get a system of functional equations. Okay, and so here it is, the system of functional equations. Now it looks a little bit complicated, so let's not worry about the details. But the point is that you have the generating function for the cylindric partition with a given profile, and you can express this as a sum over other generating functions with a profile that is obtained from your initial profile simply by removing a subset of the corner boxes. So you could remove nothing, you could remove this one, or that, or 2 of them, and so on, these 2, or all 3. And you're summing over all these possibilities, and that's what you get. So this is a system of functional equations that you can try to solve. So let's do it. Well, that's very hard. This is a very difficult system to solve. Let's do it in a trivial case when R is 1. So what does it mean when R is 1? Well, this profile, so we have these shifts. So if there's only, the profile contains only a single entry, that essentially means that we are starting to repeat the same row immediately. So, right, this has rank 1, 2, 3, 4, and then we repeat ourselves. If we repeat ourselves immediately, then the situation completely trivializes. We're back into the world of just ordinary integer partitions. And the functional equation just simplifies to this here, which everyone can solve, provided I give you the correct initial condition, and you just get back Euler's infinite product. Okay, so at least for rank 1, we can all do this. Well, it turns out for rank 2, the solutions are also known. And for example, here is just some of these solutions for rank 2. So now these profiles have only 2 entries. And you can see we get essentially, for example, these Rogers-Ramanujan functions again. If you send z equal to 1 and you drop this prefactor here, which is just like a Dedekind data function, you have recovered these Rogers-Ramanujan functions. So these functional equations really allow you to find these Eulerian forms for these cylindric partitions and therefore for these branching functions of these affine Lie algebras. Unfortunately, solving this system in general is incredibly difficult. Okay, so it's a complicated system of functional equations, and the larger the rank or the larger the level, the harder it is to solve this. So the level, if you increase the level, that's the total offset. So again, let's go back to this picture. So the rank is the number of rows before you start repeating yourself. The level is the offset between the fundamental domain and when you start repeating yourself. So if you make D or R larger, then these equations become more and more unwieldy, and it's very hard to solve it. So as I said, for rank 2, this is just 2 examples for rank 2, but in general for rank 2, it's completely solved, and I'm not going to show you what the solution is. This is just a particular example where you see these Rogers-Ramanujan functions. So I've managed to solve the equations. Well, I shouldn't say solve. I've managed to conjecture the solutions in the case rank equal to 3. So this corresponds to affine SL3. So that's really the first case beyond affine SL2 that's been solved so far. So this is still unpublished, but in any case, so I have the solution, but I can't even verify that the solution actually fits these functional equations. But you can certainly on the computer, for example, verify that the solution is correct. So that's what I did, of course. And well, these expressions look very complicated. So here is an example. So you can see now I have this profile contains 3 entries, because that's the rank 3. And the sum of these entries, that's the level. And what do these Eulerian sums look like? Well, it's just a whole product of Q-binomial coefficients and then some multi-sum. So these are Eulerian expressions, but they're very, very complicated, which makes it difficult to show that they actually satisfy these functional equations. But when I said z equal to 1, then I know I get these branching functions or characters of these W algebras, in this case W3. And so therefore we have these identities where essentially we have these Eulerian series that are equal to infinite products. Now even this looks quite complicated still. So to sort of finish up, I'll show you some of the simplest cases. So here, for example, modulus 7 identity. So it's only a double sum. And you can recognize that this quadratic form here in the exponent, that's precisely coming from the Cartan matrix of SL2 or SL3. And this is modulus 7. You can go up. Here's a modulus 8 identity, modulus 10, and so on. So there's, and of course, I have for any modulus that is not congruent to 0 modulo 3, I have such an identity. All right, so where does that leave us? Well, that leaves us with many questions. So first of all, these Eulerian sums, what do they really tell us about these modules for these W algebras? So we need an explanation. So as I said, these Eulerian sums, they usually imply some grading of these representations. And in the case of affine SL2, this is known as the principal Heisenberg subalgebra that sort of underlies what's going on. So we have some representation theoretic understanding of these Eulerian forms. For W3, it's still very unclear. what this is telling us. Well, of course, ideally, I would like to do this not just for W3, but for WR. So how to solve these functional equations for arbitrary rank. I've been able to do this for infinite level for arbitrary rank, but that's unfortunately for finite level, I don't yet know what to do. And of course, another question is, well, my solutions are only conjectural. So how do I actually prove that anything that I've been telling you is actually true? Yes, there's still a lot of work to be done and a lot of things that we don't yet understand. So, but I should probably stop here. So thanks very much.
That's great. Thank you very much, Ola. Let's unmute and thank the speaker.
Ola, I was wondering about not just higher rank, but types other than A.
Oh, well, that's a very good question. Types other than A. So at the moment in the cylindric literature, so certainly everything I said at the very start of my talk, which was a little bit rushed, but the whole theory developed by Katz and Peterson and Katz and Wakimoto and so on, that of course applies to any type. And so obviously we would like combinatorial models for these things for any type. So we know that for type A or type A not twisted, that it's these cylindric partitions. At the moment in the literature, there's no cylindric partitions for other types described yet. In the original paper by Gesser and Kattethaler, they make some suggestion what the type C analog should be, but that suggestion was made by them 25 years ago. Very recently, I asked Christian about this. Did anyone look at this? And he said, as far as he was aware, no. And he also said, oh, it's probably difficult. So unfortunately, for other types, we don't have these combinatorial models yet. So it's really, really hard to, but definitely it should exist, right? We certainly know in the ordinary plane partition case, which of course is related to classical representation theory, we have all these different symmetry classes, which indeed take you from GLN to type C and other types as well. It's definitely something that should be out there, but no one's done it.
Ola, I was wondering, how do you arrive at your conjectures?
The conjectures are really for these solutions to these functional equations. Now, the point is, when I said this variable Z, which keeps track of the max, so essentially the highest column in this stacking of unit cubes, if I set it equal to 1, which is the case where you really get characters, in that case, so for example, this W3 Rogers-Ramanujan identity, that I can prove. So of course, not using these functional equations. These functional equations really need the variable Z, because you can see it's a functional equation for this variable Z. It links Z to other value Z times Q to some power. So if you don't use this max statistic, then these functional equations cease to exist. They're meaningless when Z is equal to 1. But when Z is equal to 1, you're back into the world of actual characters. And so these character identities, I have other methods to prove them. So I certainly know that when Z is equal to 1, my solution is correct. For low values of K, I actually can prove the conjecture. It's just when the level becomes larger, you get more and the system grows. So the level is given by the sum of these entries in the profile. The profile is just these offsets. So if your offsets become larger and larger and you distribute this, right, essentially you're looking at compositions here of a fixed, right? The sum of the entries of this composition is fixed, and that's the level. If the level is 1,000,000, there's many different ways you can distribute 1,000,000 over 3, and it just becomes, it's unfeasible. But when the level is small, you can still do something. As I said, for Z is 1, I know the solution is correct. And then you can use a little bit of computer algebra and so on to verify things. Yeah, that's sort of where it's at.
Thanks very much. Let's thank Ola.